Hello everyone, welcome back to our channel. In today's video, we're taking a deep dive into a big question. Why can Junbpaw inverters achieve such high conversion efficiency? All of our inverters delivers over 93% efficiency. So what's the technology behind this impressive performance? Let's find out. Okay, now we'll use this 24 volt 3080 watt silent inverter to actually test its working efficiency. First, we'll conduct a full load test. I am gradually increasing the load power, aiming to exceed 3000 watts. Alright, the load has now stabilized at 3019 watts. So what is its efficiency? Let's calculate it. Efficiency equals total output power divided by input voltage divided by input current. Let's plug the numbers into the formula. 3019. 24.3, 131.3. Okay, the result is 0.941, which is 94.1%. This is the working efficiency of this 3080 watt inverter under full load condition. Next, we'll adjust the load to around 1500 watts, which is approximately half load, to see how the efficiency changes. Alright, the load is now stabilized at 1588 watts. We'll use the same formula to calculate. 1588, 25.08, 66. The result is 0.959, meaning 95.9%. This is its working efficiency at half load, reaching 95.9%. Why can our product achieve such high efficiency? The answer lies within its internal structure, the 1080 model, the 2080 model, and this is the 3080 model. None of our products use traditional wires for conducting electricity. Instead, they all adopt this busbar structure. The interior of this 3080 Ti uses a total of 13 busbars. Each busbar is meticulously arranged to collectively provide efficient power supply for the inverter. This is the fully disassembled 3080 watt component that I deliberately laid out flat. And what I am holding now is its fully assembled structure. Let's take a look at the path of the current. This wire is the positive terminal, which is directly connected to the terminal post. This one is the negative terminal. The negative terminal, there is a row of built-in fuse links. The current starts from the positive terminal, goes to the transformer, and after passing through the transformer, it travels via 4 bars, combined with a switch tube circuit to reach the negative terminal. This design achieves minimal impedance, then undertakes a dual task, efficiently conducting electricity and enhancing heat transfer. For effective cooling, the main power current is handled by 13 busbars, while the control circuit and signals are managed by the PCB. The current flows directly to the transformer through busbars. A key aspect of our design is that the distance between every 2 transformers is precisely equal. This means the impedance from each transformer to the positive and negative terminals is identical, ensuring balanced power distribution and heat generation among them. Thanks to this symmetrical and direct structure, impedance losses along the current transmission path are minimized. If we were to use wires to carry the same level of current, the cross-sectional area of the wires would be insufficient. In case of overload, wires will become the weakest point, most prone to overheating and fire hazards. Therefore, we have fundamentally re-engineered the design concept, complete elimination of wires. Both our 1080 watt and 2080 watt models adopt this specialized copper busbar structure. You will not find a single internal wire even in the output stage. There are no fly leads whatsoever. Next, let's move on to the transformer. First, a key specification. The PQ50 transformer has a maximum power of 3000 watt. This performance is achieved through our interleaved busbar winding in the primary coil. Unlike traditional enameled wire, the design ensures 1. A large conductor cross-section, 2. Higher magnetic induction density. Now, for a live measurement. Width 8 mm. Single layer thickness 0.65 mm. 5 layers per side, with an interleaved structure equivalent to 10 conductive layers. This ample conductor material guarantees high power capacity and efficiency. Okay, let's calculate its total cross-sectional area. 8 0.65, 10, which equals 52 square millimeters. If we calculate based on 5 amperes of current per square millimeter, then 52 multiplied by 5 gives 260 amperes. This means the positive coil can carry a current of up to 260 amperes. This primary coil is guaranteed not to exceed 120 degrees Celsius. The insulation material wrapped around it can withstand temperatures as high as 180 degrees Celsius. All the materials used here are high quality, high temperature insulation sheets. In our 12 volt 3080 watt unit under full load, each transformer only carries 130 ampere of current, which is half of the design capacity, providing a 100% safety margin. This critical bus bar has a width of 25 mm, a thickness of 1.54 mm, and thus a cross-sectional area of 38.5 square millimeter. Over a short distance, it can carry 7 ampere per square millimeter, resulting in a total current capacity of 38. 5 times 7 equals 269.5. Even at 269 ampere, the temperature of the bus bar remains below 60 degrees. Therefore, our design is not only excellent, but also highly rational. So, behind the high efficiency, safety, and full rated power lies our meticulous, full-link engineering from the transformer to the entire circuit. In the places you can't see, there is only uncompromising quality and purposeful design.